Good morning.
Morning, Doug.
How's everyone today?
Pretty dang good myself. How about you?
Ah, doing great. Thank you. I'm ready to rip. I looked up and it's like, oh my God, it's 8 o'clock. Where'd the time go? Let's see. So let's give you guys a freebie here that showed up on time. Whoa, look at that. Let's see. Delete, delete, delete. Stop. This is just playful, just because it occurred to me while I was thinking about all the things that we've been talking about, and the fact that you can spin things around and so forth. There is a program. I have an app on my iPad here, and I use this in Calc 4. So I've only played with it sort of one term, but you can actually graph 3D things. And I thought of this because I think it seems like Eve found it, or at least I saw something she turned in that had one of these drawings on it, and I was like, oh, that's right, GeoGebra. But this is 3D GeoGebra. So here's what happens when you take calc to the third dimension. When you take, well, just take graphing to the third dimension. So now you have an X, Y, and a Z axis. So I'm going to say Z equals X. Let's see. Nah, let's even throw a number in front of it.
Yeah, anyone that's taking physics should be used to the Z-axis.
Yeah, good point. It's kind of a mind boggler. Enter. Let's see. Do I have to? I can't remember if I have to tell it what A is first. This program's a little clunky. Enter. Yeah, it doesn't like that. Delete. Should have just left well enough alone. So this is kind of what this machine's version of a slider. If I go in there and I say A equals 2, for instance, now I can make A 2, 3, 4, 5, 6. But I'm going to graph something we've been studying, and then I'm showing you this for a reason today, because we'll probably start off with this problem. But if I say, okay, now let's let Z be equal to A, which is now 2 times the statement x squared plus y squared. And I close that parenthesis off. Notice the shape that you get. This thing is really cool as an app because you can just put your finger on it and kind of spread it around. So you're actually getting a 3-dimensional graph, and you can't really tell, but that's not a solid, that's hollow. And what's kind of cool about A is that A does what A always did, which is steepness. I wonder if, let's see, settings. I wonder if there's other colors that will do better here. Let's see, I don't even remember how to find color. Is that color? Light color, blue, green, doesn't seem to matter. So I don't know if you can picture that, but that shape is actually hollow. That's not a solid. This shape is called a paraboloid. So it's what we've been doing, and it's just kind of neat to visualize it a little bit. The problem is you don't get to watch it kind of spin its way around. But in a sense, you're just taking a parabola on one side, and then you're spinning it around in a circle. And does it make sense if you're spinning a parabola? And this is, again, why your book was a little, I don't know, definite about the way it said it. If you spin just a line that's a parabola around, does it make sense it's going to be hollow? So that's why the book said, because we've always been finding volumes, the book said, consider the parabola bound by y equals 0 and x equals 7. So now we have this little area over here, and spin that around. Well, if you spin an area around, does it make sense it's now solid, it's not hollow? And so if you spin a parabola, you don't have any volume. Now you could think of this as a cup and you could say, you know, I'm going to fill it with something. That's just kind of cool. So there is a way to graph things 3D. Desmos doesn't have that capacity yet. I wonder if they're working on it, because it'll be better than this if they do, because this is a little bit cumbersome. But one of the reasons I'm showing you this today, besides the fact that it's just a little bit interesting, is that that's what we're going to talk about today, is the surface area of that shape. So, you know, if I was going to build this with a 3D printer or something of that nature, you know, how many square inches of area is on the outside of that? Or if I'm going to paint it, how much paint do I need on the outside to actually paint that thing? So we've only been talking about the volume of it, which of course is very practical. If I was making a cup or a bullet that was kind of this shape, I would be, you know, using brass or filling it with liquid, and I'd want to know how much that cup would hold. Whereas now we're saying how much surface area of paper or metal or whatever would it take to actually build that shape. So that's the plan. So but we have a couple of days to talk about this, and before I just launch into that, anything that you want to ask about the project, because you suffered away at it a little bit yesterday and now you have questions? Because I would like to, as much as I can, give you some time to ask about it. Certainly you can ask about it after class 101, but why isn't my pen working? So 6 point. I just charged my pen. Why isn't it working? So let's consider the surface area of this thing. All right, I guess you'll have to wait till after class because you did not ask any questions. Let's consider the surface area of that shape. And we don't need to, the interesting thing is this was nice to visualize because we can actually see the shape that's spinning around here a little bit, but we don't have to have a 3D equation, an equation that's got an X, a Y, and a Z. We're just visually doing that. We're saying we're going to take a parabola and then we're just going to spin it around, and then we're going to ask about its surface area. So cool. Okay, Pen, I need you to write. Okay, good. And as I said, we do get to do this for 2 days. So we have today and Monday to talk about this, which means you don't owe me the 6.5 homework until next week, which is great. And this here guy is called a parabola, except for when you spin it around in a circle like this, it changes it to a paraboloid, Yeah, I think that's right. Paraboloid. So that's kind of cool to think about. Well, let's consider that. Let's just keep this as simple as possible. And let's see if we can figure out kind of logically what this formula would be, or like what's it going to take to do this. And it isn't very much different than what we've been doing. And you'll see in a minute why it followed right behind arc length of something. So let's take the equation. Let's just keep it really simple and make it y equals, well, let's at least go half. Let's say y equals 1/2 x squared. And again, just like the a in the previous problem, since I made a little bit smaller, that opened that shape up a little wider. Same thing is going to be true here. This is very close to the same thing. Actually, let's just make it match the one that's above. It was 0.4, so 0.4 is 2/5. Let's just make it match the one that's up there. So this is exactly the same equation. And if we took this graph and let's say from X is 0 out to X is, let's see, we'd like this to come out nice, wouldn't we? How about 5? I wouldn't like that to come out as a whole number. If I put 5 in for X there, 5 squared is 25. 25 divided by 5 is 5. 5 times 2 is 10. So this is a Y coordinate of 10. So my graph would look something like this. And since we're stopping at 5, and when I plug 5 in, I get 10, then that's kind of the parabola shape. But this time we're not saying, hey, let's fill that in. Let's think of that as a solid. We're not kind of coming in here and saying, let's rotate that around the y-axis and figure out its volume. We're saying, no, let's not do that. Let's just leave this thing alone. It's just a parabola and spin it around. And if we do that, we get that hollow shape that I graphed up there. So what we'd like to know is, well, what is its surface area? Well, let's play with the shape a little bit. This isn't terrible. What happens if I take a little chunk of this right here, let's say, and I spin that around the axis? And so if I spin it around, I think you would agree it looks something like this. That's not bad. It's not bad either. It's not terrible. So if I took this little tiny slice of it right here and I did the same thing, wouldn't it kind of look like this? It would be the same little chunk over there. And then the top of it would look like that. Do you agree with that? So I'm thinking about this slice, and I guess I'm interested from our previous logic that you see why I'm slicing it this way. If I slice it this way, I'm going to have slices just like that. As they move up, of course, they're going to get larger. But it's the same slice the whole way through it. Whereas if I slice it vertically, that's going to be a weird shape. It's going to be a parabola that actually changes equations as I move through it. So I want to slice this horizontally since I spun it around the y-axis. And so what I really need is, well, the area. I need the area of that little slice right there. So I want to give you a second to think about that. In the sense, isn't that really similar to cylindrical shells? Like we used it to find volume, but that slice is kind of like cylindrical shells because it's hollow. So we're not considering this as a solid. Do you understand that? We're considering it as a kind of a stripe. And so if I kind of cut it, if I cut and stretched it out, wouldn't it look something like this? So this is why I say it's kind of like cylindrical shells. So what I need is the area. What I need is the area of that shape right there. Well, notice it's kind of a rectangle.
But wouldn't the long side be like pi r squared because it's circumference of that circle?
That's right. So isn't this length right here just the circumference of the circle, just like it was for cylindrical shells? And isn't that 2 times pi times radius? So that's true. But notice the sides of this are, well, they're angled. Does that make sense? So that length right there is not just dx. It's a little longer than that. Do you see what I'm saying? Because it's at an angle. It's
Would it
not
be
straight up
D,
and down.
would it be DX DY?
Yeah, and
No,
this is
that's-
where yesterday comes in. If it's not DX, since it's sideways, what did we do yesterday to come up with the length? Didn't that what we did yesterday? We said, hey, there's a little length here, and we'll add it to a little length there, and we'll add it to a little length here. Isn't that what arc length was? We found a representation for that little length.
Yeah, it was the square root of 1 plus that, whatever it is, squared, right?
Yeah, and let's just remake this from yesterday. If I take that right there and just kind of blow it up a little bit, didn't we say yesterday that this is a little bit of Y perfectly vertical? That's a little bit of X perfectly vertical. So we said this right here was the Pythagorean theorem of those two. So that's really what that is. That's the length of that little chunk. It's really the square root of dx squared plus dy squared. But we saw yesterday that, or day before yesterday, that was like, we don't really, that's hard to work with. So again, just as a reminder, we said, well, let's take that statement. Let's just rebuild it again real quick, just to grow our intuition. Let's take that and multiply it top and bottom times dx over dx. And if we move that bottom dx inside the square root, in order to move inside, it would have to be squared. Notice the square root of dx squared is dx. If I took it out, it would be out there again. And then that would just leave. So in a sense, the bottom one went there. And then this top one is just out there. And then we said, hey, look, I can actually divide those. If I take dx squared divided by dx squared, I get 1. And if I take dy divided by dx squared, and I can square them beforehand, which is what it shows here, dy squared and then dx squared and then divide, or I can take dy divided by dx and then square it later. That's what we decided yesterday. Let's take dy divided by dx, and then we'll square it afterwards. And then there's that little dx outside. That's a better way to say it. So that, my friends, is what this length is. So it's just arc length. And again, we said this looks better. I know what to do with this because, hey, isn't that just a derivative? So I can do something with that. So if that's true, and notice, I don't know if you can picture this, but like all the way around this slice, I'm making it look like those slices are vertical, but they're leaning out all the way around it, aren't they? Like as you go around it, isn't every single one of them leaning outwards? Take a look up here. Isn't every single, if I start here and kind of go around the outside, aren't all of those slices leaning outwards? Like every one of them is kind of a hypotenuse. Does that make sense? It's kind of hard to visualize. So isn't that area then just equal to 2 times pi times r times this glorious arc length square root that we invented for ourselves? Yep. Now, notice in our case, this is around the y-axis that we went here. And so because we went around the y-axis, isn't the radius actually x? So I could modify this by just doing this. If I said x there instead, and I just added the note, this is what we do for around the y-axis, if we're spinning something around the y-axis. That's kind of our formula. This is our formula for surface area, or just area. You
So
see
if
how
we
close that
wanted
is to cylindrical shells? It's real similar to that. Now, part of that is good because you think, oh yeah, okay, I see that that's really closely related. But honestly, that's only good if you actually understood cylindrical shells. If you found yourself stealing the formula out of the book, then you probably think, well, this formula is really similar. And now I'm going to take a test here in a week or so. And then I've got, cylindrical shells problems, and I got these surface area problems. And now I got all these formulas, and it's like, I'm losing it. That would be normal to sort of feel that way a little bit. But that's why I think it's so cool to be able to, I don't know, kind of build these things for yourself. Just draw pictures and reason it out.
So Doug, I had a quick question about this.
Fire away.
If we were gonna be rotating this cup around the x-axis, would we multiply the square root of dx squared plus dy squared by dy, or yeah, dy over dy instead of dx over dx?
Yeah, in other words, you're asking this really good question. Like, what if we spun this thing around the x-axis? What would happen? Well, that's actually a good question. Why don't we just do that next and see what happens? Let's try that.
I was thinking in my head though, like I think that's the only difference we're gonna have, right? Like if we had this exact same equation, the only difference is we're multiplying dy over dy.
You're right. Yeah.
Okay, cool.
Yeah, that's right. If we go around the other axis, this is not going to be very different. So your intuition about that, right, Connor, is right on. So good for you. So notice this is, if you will, kind of already all in x's. Like this is x, this is x. Well, this is the derivative of, y with respect to x. That was another way we wrote derivative. In other words, that's the y equation, but we're taking the derivative and getting an x answer for it. Does that make sense? So for our parabola then, so for our example, we'd say, okay, cool, I got everything I need. Now, of course, the only other thing I got to add to this is really just the area of one slice. But what is integration good for? Integration is good for adding lots of slices. And of course, my slice needs to be really thin, which is going to cause there to be a billion slices. So as we've been understanding, what integration really does is add infinitely many, infinitely small things. And again, that's what's implied by this dx here, or by this dy dx, is the fact that this slice is tiny. It is infinitely so small that it sort of doesn't even matter. It's so skinny. Well, that means there's going to be a billion of them. So we've got to kind of take this to the next level and say, awesome, well, I'm going to actually add all of these up. And you may remember that, hey, 2 pi is a constant. I could pull that 2 pi out front if I wanted to. And if you look in your book, they could even write this formula that way. I'm sure this is in a box in your book somewhere and all boxed in, and take a look at this. This is really important. That 2 pi can come out front if I just don't want to get distracted by it. And so maybe the formula even shows that. So notice again, I'm working with x's. And so I'm not looking at the 10, which was the y coordinate. I'm looking at the 5. Who can tell me why this is not true? That's logical to think that, doesn't it go over here to -5? Why wouldn't it be from 5 to -5? Well, notice the x here is our radius, isn't it? X is our radius in this picture. And part of me says, well, it doesn't even make sense to have a negative radius. And, by definition of what we even wrote here, we're thinking of it as spun around. And so really the graph only exists, right here. I mean, that's the graph we're spinning. So it's actually not from there, it's from 5 to 0. I don't think that's obvious. That's why I pointed it out. And then all the rest of the stuff. So I've got an x left behind. And then I've got the square root of 1 plus, this is what I said you should just write every time. Notice I wrote everything out except for, well, what's dy dx? What's the derivative of this statement up here in terms of x? That's a relatively easy derivative to take. Power rule, bring the 2 down front. Notice again, we're getting confused because we're going backwards and forwards with the power rule, but this is a derivative, not an integral. So I'm not adding 1 to the 2 to make it 3. I'm doing what derivatives do, which is I take 2 and multiply it by that. So I end up with 4/5. And then I take x to the second and reduce it by 1 power. So now it's down to x to the first. So there's the derivative, the slope of 2/5 x squared. There, I'm done. Now, as we said with respect to arc length, a lot of times because of the complexity of this statement right here, because of the complexity of that statement, you end up with integrals you can't take very much. Is this one of those? Is this an integral we can't take and we should just cheat? If I gave this on a test, am I going to say something like evaluate the integral using software or using your Texas instance calculator? Or is this one that I could say as a teacher, no, do that one by hand?
Well, there's an x outside of the square root that'll cancel.
Yeah. Remember how when you have a statement inside here, we don't like the fact that there's a square root with an ugly squared statement inside here. But remember when this statement here, x squared, its derivative is sitting out front. This is a form fit substitution problem. So this is one we could actually do. We don't have to cheat on this one. So let's practice that. At least I don't think so. So let's keep going. Let's see, 2 pi, that comes along for the ride. I haven't taken the integral yet. The only reason I'm rewriting this is because I actually want to square what's inside there. 4/5 x squared, that'd be 16/25 x squared. So the substitution we're always looking for is to simplify things. And so my gut reaction, or the classic substitution here, we don't know for sure if this is going to work, but the classic substitution would be to let u be whatever's inside, because then that would just be the square root of u. So that's going to get rid of this. Awesome. What about this dx? Well, I'm going to have to take the derivative of both sides of this. Derivative of 1 is nothing. Derivative of 2, the 2 comes down front, so that's now 32/25, and that's just x. And then the derivative of x is the derivative of x, just like the derivative of u is the derivative of u. So then if I solve that for dx, I would divide du by x, and then dividing by 32/25 is the same as multiplying by 25/32. So there's what dx is. And now I got everything I need. Well, not quite everything I need. Let's go ahead and keep going with the 5. So with the 5 and the 0, x equals 5. What's that going to produce? 5 squared is 25. Hey, that's cool. Divided by 25 is gone, and you have 16 plus 1. So u is 17. If x is equal to 0, again, your gut reaction might be u is 0, but if you put x is 0 in there, you get 0 plus 1. So now I have everything I need. So the 2 pi comes along for the ride. Instead of 5 to 0, because I decided to switch into u land completely, now I have that x out front, and I just have the square root of u. That's very wonderful. But then dx gets replaced by this crazy statement, which is 25/32 times du over x. And now we see what Cheyenne noticed early, and what I'm hoping a lot of you noticed yourself, hey, look, the derivative of this x squared term is sitting out here, which is exactly why when we get to the place we are, we can go, sweet, those two cancel out. And so I didn't have to get rid of that x up front. It got rid of itself. If that had been anything other than x out there, if it had been x squared, we'd have been hosed. Like, this problem isn't doable, at least with what we know. X cubed, we're hosed. X is not there at all, we're hosed. Very hard problem. Except what's inside is squared, what's outside happened to be x. Those just canceled out. And the 25 over 32 can pop out front. I guess that would be 50 pi over 32. Of course, I could reduce that. And then all I really have here is from 17 to 1, I've got u to the 1/2 du. I substituted, and that made a problem that was horrible looking easy. So you look at the two red problems. The original one, terrifying. I see everything that I hate up here. Do you see all of it from derivative land? Look, junk times junk. That's product rule. Except integrals were going backwards. And then I got square root of junk, junk inside of junk. That was chain rule. This is like product rule and chain rule in one problem. And so by substitution, we were able to change this thing into a super simple, easily defeatable integral. So again, that's just good practice. So let's see, of course, this is easy. I will reduce 50 over 32 because I can to 25 pi over 16. If I take the integral of u to the 1/2, I get add 1 to the exponent, divide by 3/2, which is multiplying by 2/3. Now I can evaluate that at 17 and evaluate it at 1. And so I get 25 pi over 16. If I stick 17 in there, ooh, that's terrible. By the way, you could even pull 2/3 out of the front of this if you wanted to. I think I will. So now I have 17 to the 3/2 minus 1 to the 3/2. That's horrible. Again, you should know from your previous algebra knowledge, what does that 2 mean right there? What does that 2 tell me to do this number? Because it's on the bottom of a fraction.
The square root.
It's a square root. And so 17, well, dang, you can't take the square root of 17 without a calculator. This one's nice though. 1 to the 3/2, the square root of 1 is 1, and then 1 to the 3rd is 1. So this is actually just 1. So you could play around with this and, rewrite it as the 17 times the square root of 17. There's all, creative things you could do there, but I'm going to quit with this answer. Let's see, 2/3 times 25, that'd be 50 pi over 48. So 2's cancel. I should have thought that beforehand. I might as well just write this simply. The 2's cancel, so you end up with 25 over 24. And then I end up with, I'm just going to leave it alone, 17 to the 3/2 power minus 1. I'm going to quit right there. Nobody told me I had to write it any certain way. I'm not going to tell you on a test. Again, I consider that to be a really useless number because notice it has pi in it, which is some crazy decimal. It has a ridiculous fraction, 25 over 24. And then it's got square root of 17. And so, this is useless. In the real world, nobody wants this for an answer. Good for you, math nerd, you got it exactly right. But, we want to, it's nice to be able to turn this into a decimal just because this is actually supposed to be the area of something, right? So for me, it's almost irresistible, which makes me a non-mathematician. What am I typing in my calculator for 17 to the 3/2 power? Read my mind. I'm lazy. What am I typing in?
Would it be the square root of 17 to the 3rd power?
Yes, that would work, except for I'm lazy. It's too much trouble to type what you just said. You're right. I just raised 17 to the 1.5 power. Like, it's a lot easier to type in. I know that doesn't focus very well, but if I want a decimal, so I got approximately 226. And remember, this is an area, so I'm going to write square centimeters, even though there was nothing saying that our squares in our graph were centimeters. I just hate square units. Just remember, this is an area, not a volume. Everything in all of our previous assignments, we were always finding volumes of things, so it was like cubic centimeters.
I'm gonna
Again-
put the,
Go ahead.
I was gonna say, I'm gonna put the argument out there that 3/2 is just as easy to type in as 1.5.
If your calculator is structured to handle that, which this one is, then you're right.
Yeah, that's, yeah, if you're,
But if you type 17 raised to the 3 divided by 2, then that doesn't work. That's my only, you have to put parentheses around it, so forth. So
right.
that's what I was thinking when I said that.
No, yeah, that makes total sense. Most calculators are like that, but the TI-84 is when you raise it, it just lets you type whatever you want in that exponent.
Yeah, while you're up there. Yeah, you're right. You're absolutely right. I'm glad you pointed that out. Now, I don't know about you, but I don't really have any. In my case, I went really slowly and I have all of you watching, so I'm pretty sure I'm correct. But notice how hard that is to check. Like, does that even make sense? I mean, I got 200. Is it 2,000, 20,000? Like, I don't know. It's very hard to estimate, isn't it? I mean, the only way I think I could estimate this is to go back and say, well, I know what the volume of a cone is, and that's conish. And so I could find the volume of a cone and see if I got an answer that was a hair bigger than that, right? Something like that. That'd be kind of cool. But man, I got to kind of trust the process, don't I? Did I go slow enough that you're able to kind of take that in as I did it? I try to go slow and give you time to think as much as I can. Is there anything about that process that bothered you? Obviously, we spent everything I'm showing you right now is just review of things that we kind of learned in the past. The most important part of this is just setting the dumb thing up in the first place.
I do want to ask if we do have to cheat on a test or something, so we don't waste our time or anything. Will you say use your calculator to
No.
cheat?
Yep. I'm going to tell you on the test, evaluate this by hand, evaluate this with a calculator. I'll make the key first, and that way you don't have to waste any time, because you could spend an hour trying to evaluate this, right? You could spend 2 hours. So I gotta be really careful. All right, let's try this around the other axis. Yeah, let's just leave the same equation. I was going to throw the 2/5 off of it because that was kind of a pain, but let's leave it. So blame Connor. This is Connor's fault. We're doing this. No, it's not. I would have wanted to do it anyway. Notice my drawing is not to scale because what I called 5 and what I called 10 are about the same size. But what I'd like you to do is see if you can set this up yourself. So I'm going to conceptualize this a little bit for you and attempt to draw it three-dimensional. So the important thing here is this. This is the original equation that we spun, and it created the other shape. And so if I say beautiful, I want to know what the surface area is. I'd like you to try to set that up just based on the logic that we just used a minute ago. And I will also go back and draw for you a slice of it, because maybe that will help you a little bit. There's your slice. So this equation hasn't changed. It's still y equals 2/5 x squared. And you may be able to tell by looking at it, we're not going to get the same answer to this. This is much smaller. It's kind of like a concave cone. You may remember I showed you a drawing of a house plan that I drew that had this arrangement on it. We found the volume of it earlier, but now we're saying, what's the surface area? And by the way, notice that's a really practical problem. I just had somebody call me on one of my house plans yesterday and say, hey, what's the surface area of that roof? Because I got to order all the roofing for it. And, you know, because I know calculus, I can answer that for this question. What's the surface area of this roof? How much metal am I going to need to cover that roof? That's kind of cool that you can figure that out. Try it yourself. Screw it up. Then whatever I show you, maybe it'll mean more. What would you rather see? Would you rather see this example? I probably should put that example up there. Can't really show both of them to you at the same time. I'll go back and forth a little bit, maybe. Don't evaluate the integral this time. Let's not waste the time to do that. If you get the integral written out, just quit right there. Maybe jump to Desmos or your calculator and cheat and ask it to evaluate it or something, but let's not waste the time to actually evaluate it this time, even if we can. Let me go back to the other drawing now. All right, let's do it. So as before, we've got that little length right there. We've been calling that little length 1 plus dy dx squared dx, right? So we've been calling it. So the only other thing we need really is the radius. What's the radius of our slice here? What do I call the radius of that slice? I hope every one of you knows the answer to this question. What's that radius right there?
dy. No. Yeah,
It's just y. It's
just y.
So y. Then when you slide this shape over here, then y is really short. When you slide it over here, it's really long. Do you see why it has to be a letter? Because we need this slice to slide all the way through this thing. It can't be 6 or something like that. But it's a y coordinate, not an x coordinate. When I look back up here at this original problem, that radius was an x. So when I spun it around the y-axis, the radius was x. When I spun it around the x-axis, the radius is y. And again, when I slide this little slice up here, notice the radius is huge. The radius is big up here, it's medium-sized here, and it's teeny tiny down there. So you just need to see that as a coordinate. It's just a y coordinate. So there's the radius. And then to get the circumference, don't forget it's 2 times pi times radius. And so it's kind of like the same formula. So the area I don't know what to call this thing. I'm going to call it a stripe, a strip. The area of our stripe unrolled would be 2 times pi times radius times its height. But its height is slanted this time. So I'm not just saying 2 times pi times radius times height. I'm saying 2 times pi times radius times this statement right here. Isn't that the area of our stripe? Now this is where it gets kind of interesting. What's not so good about this problem?
You got Y's and X's.
Beautiful. You got Y's and X's. And so that's not so good. We don't like that. We don't want that. Is that easy to get out of here or not easy to get out of?
Can't you just set the equation so X equals Y? Like you have it solved for Y, can't you solve it for X and switch it?
Sure. Like remember that this is our kind of equation that allows us to transfer from X's to Y's. So there's a couple of things you could do with this. This problem works just like it is. Like this. In other words, couldn't I replace, since we're sort of stuck with dx here, couldn't I just replace y with 2/5 x squared? Now it's x. And isn't the derivative of y with respect to x we just saw a minute ago, isn't it 4/5 x? So now it's all x's, right? Correct. Works great.
Wait, but didn't we need a regular X in front to like cancel? So wouldn't that, because it's now an X squared, wouldn't that be problematic?
Yeah, let me write this out and see if you all understand what Eve just said, because she is right. We're in danger this time. 2 pi times y, which we're now replacing with 2/5 x squared, and that means I could even pull the 2/5 out front. And then this is square root of 1 plus 4/5 x squared dx. And we're working with x's, and so the x's for this are still between 5 and 0. Does everybody understand what Eve just said, though? Can we take that integral? We're in deep trouble this time because the x squared under the radical sign does not have an x outside. We are not going to be able to take that derivative, not without being better at integration. So if I put this question on the test, I would say evaluate it with your calculator. So I'm going to do that really quick. And I'm going to put the 2 pi back in just so that I can type the whole thing in there at once, because I don't want to multiply by 2 pi later. So I'm going to multiply it back in. So that'd be 4 pi over 5 times x squared. Maybe you do this with me to make sure we don't blow it. 4 pi over 5 divided by 5, and then I say x squared, and then I say times the square root of 1 plus 16/25 x squared. Seems easier to type. 16 divided by 25 by 25 x squared. So I've got that whole thing typed in. I hit graph. I get some graph. I don't really care what the graph looks like. By the way, I'm expecting the answer to be less than 226. I'm not sure because I didn't draw this to scale. Remember that last graph was actually 10 tall. So it's pretty tall. So maybe I don't even have a clue. Maybe I don't even know what to think. I'm just going to see. So I say second calculate. I say evaluate that integral from 5 to 0. And I get 332.7. And it's a good thing I qualified what I said, because I was thinking this would be smaller, and yet it's actually bigger.
Wouldn't it be from 0 to 10 because you're doing it from on a different axis?
Yeah, good question. And the answer is no, because we're still dealing with x's. In other words, my equation was made of x's, therefore my limits of integration have to be x's. And so this graph existed, this dark red graph over here existed from x is 0 to x is 5. So that's why it's only x to 5. Now, if I somehow figured out how to do this with y values, then it would be 10 to 0. But I'd have to be using y values to bring that about. Does that make sense?
I think that's what I started doing. I switched everything over to Y's and I wrote out something completely different.
And we may be going that direction right now. Now, there is another option to this, which is why I called that option 2. And so let's consider that for a second. Does it make sense that if you have a, let's see, if you have a little stripe of graph right here that we already said that was the same as dx squared plus dy squared. But watch what I'm going to do now. This time I'm actually going to multiply it by dy over dy, not dx over dx. If I did that, I'm going to get dy squared over dy squared, which is 1 again, but I'm going to get plus dx squared over dy squared, which means it's not dy dx, but dx dy. And there's a dy left outside. Why is that bothering me? This is okay too. In other words, your arc length does not have to be sort of in terms of x, it could be in terms of y. What does
So
that
this
mean?
is not the axis of rotation that determines it, because you can just solve that out. It's the arc length that's going to determine it.
So what's interesting about this logic, because Logan was just talking about, you know, which axis are you rotating around and so forth. It has to do with how easy is it to convert this. In other words, y equals 2/5 x squared. That's pretty easy to solve for x. I can multiply both sides by 5/2 and take the square root. But does it make sense if this had a plus x on here? I would not be able to solve this for x. That'd be very hard to solve for x. And so some equations are easy to solve for x and some of them are not. But I just want to see what would this look like if I took that approach. So let's just copy the area of our stripe down here and reconsider it. So it hasn't changed. I mean, the radius is still y. Do you understand that? It's just now that we're going to say is, no, let's just replace this whole thing with, instead, we'll still have 2 pi y, but we'll have 1 plus dx dy squared dy. Is that better? We'll notice we don't have to do anything with that y now. Remember before we had to switch it with 2/5 x squared, we can just leave it as y because we're in y land. So now everything is y's. But this is a bit of a stretch in your brain, I think. How are you going to do that? What does dx dy mean?
It's the derivative with respect to y.
Yeah, it's the derivative of x with respect to y, which basically means we need to take our equation y equals 2/5 x squared, and we need to solve it for x. So if I multiplied both sides by 5/2 and took the square root, then I could say x equals the square root of 5/2 y. And so dx dy, meaning the derivative of x with respect to y, notice the square root, the 5/2 just comes along for the ride. So I have the square root of 5/2, but then the square root of y is really y to the 1/2 power. So the derivative of that would be 1/2 comes down front, and now y is to the negative 1/2 power. So I guess I could write that as, I don't know, does this confuse you? I'm just trying to clean this up because remember I have to put it in back here and I have to square it. So I'd like it to be I'd like it to be as nice looking as possible because I don't just get to write it in here. I got to square it. So let's do a little bit of algebra. If I put this 1/2 inside, wouldn't it become the 1 gets squared and the 2 gets squared? Is that worth doing? No, let's just leave it alone. And then it'd be well over the square root of y. And so this feels like a terrible idea to me. Like this is more trouble than what we did a minute ago. But if I plug that statement in up here, I do get to square it, which means all those square roots go away. And so maybe this isn't as terrible as we think. I'm not sure. I purposely never plan ahead for that reason in this class, so that we can just think out loud. Now to, I think it was April's point, this time because we're talking about y, doesn't this graph exist from y is 10 to y is 0? So since I'm working with y's, I have a different limit of integration. So I'm saying 10 to 0. And there's a y there. And I have the square root of 1 plus, well, what is that squared? I guess that'd be 1/4. Maybe I should work that out down below. So if I take that statement squared,
It'd be 5/8 over y.
oops, I'm just going slow. I hear what Justin said, but I haven't done it yet. So I'm just going to do it and see if I get the same thing he just said. Wouldn't it be that? Yeah, 5/8 over y. Justin's right. So I just squared everything. So 1/2 squared is a 4th, square root of 5/2 squared is 5/2. So I get 5/8 over y, or 5 over 8y. How about my previous question? Can we do this? What do you think?
Yeah, but it seems kind of similar to the last one.
It's similar to the last one in the sense that, you know, this, I'm not sure is my honest answer right now. This y is not just a y, it's on the bottom. It's really y to the -1. So, you know, that's, and its derivative is not out here. My gut reaction is this is going to be hard. Maybe we could do it. I should say maybe I could do it because I do know some of the tricks I'm going to teach you later in this class. So I'm not sure. But let's not and say we did. Like, let's just type it into the calculator. Now what I'm hoping very badly that I get 332 again, because I haven't seen that I made any mistakes. And if I don't, then I'm thinking, uh-oh, I'm not really sure what just happened there. Now I can't type y in my calculator, so I'm replacing those with x's, but I'm going to go back and rewrite what I just did. So let's see, I have 2 times pi times y, 2 times pi times x. And then I've got the square root of 2 times pi times x. Square root of 1 plus 5 divided by 8 divided by y is the way I'm going to type that. Don't type 5 divided by 8 times y without parentheses. I'm going to type 1 plus 5 divided by 8 divided by y, except for I'm going to put x there. And I graph that. And I ask it, what is that area?
I got 332.
Oh, thank God. TI says, I almost don't want to type it in just in case I don't get the same thing.
Yeah, I always find it so much easier to type it into Desmos.
Yeah, Desmos is way easier. Now, again, I want to caution you. What I'm trying to do here is teach you how to think, teach you that the book is not going to teach it this way. The book is not going to sort of give you two ways to do this. What I'm trying to get you to understand is both of these statements, this statement right here, and the other version of it, they're the same. Use whichever one you want. You can put them in independently, no matter which equation you're working on. That's a statement that will tell you, but you just got to understand what dx dy means. It means you need to solve for x. If you need to solve for x and the equation is something really ugly, like y equals sine of x, you would not want to use that one because solving for x is sometimes ugly, sometimes downright impossible. So those are equal statements. Let me highlight that point while you're trying to soak that in.
Equal statements that make
Equal statements for this little curve. The length of that. What's the length of that curve? Two options. Either one. Amazing. It's either the square root of 1 plus dy dx squared dx, or it's the square root of 1 plus dx dy dy. Which one do you prefer? Or do you?
dy dx.
Yeah, you probably prefer, at least I do. I prefer the top one just because I'm used to it. Like isn't that how you're usually given equations? I mean, you can't, without Desmos, you can't even graph equations that are x equals. You can only graph y equals. And so you're used to y equals equations. Therefore, that top one is sort of better. And as far as what you see in your homework assignment, maybe there's some curveballs in there, but you're not going to see curveballs on the test. Like I'm going to give you good straightforward stuff and, you know, kind of normal equations, y equals x squared plus 2x or something like that. Okay, let's do a couple of cool things here. At least one of them, maybe we'll have time for both. And then what I'd like to do on Monday is maybe do a little more direct prep for, say, the homework assignment. Like maybe there's some curveballs in there and we'll have time to talk about them. Or maybe, you know, I just want to give you a bunch of examples, but I just want to show you a couple of cool things. Here's one of them. Like, as I've been mentioning, this is what calculus really gets used for. Formula for the surface area of a cone. We have a formula for that. You don't have it memorized. You don't know what it is off the top of your head. But we have an algebra formula for that, and calculus gave it to us. Let me see, do I still have it someplace? I'd love to show it to you really quickly if I do have it. Calculus notes, geometry. Let me see if I have it. This won't take a second. Did I leave it in the calculus school drive? Cha-ching! I did. So here's a reminder. This is the set of formulas that's sitting inside. Bam, there it is. Surface area of a cone. None of you had it memorized, right? Probably have used it even so little. There's some of you probably would say, I never even saw that ever before. But stare at it for a second. What part does this pi r squared play in the surface area of that cone? You should recognize that. What's that?
Is that the circumference?
No, close. Where have you seen pi r squared before?
It's the area of the circle.
That's the area of the circle. So that's the area of the bottom of the cone. Does that make sense? So this part over here is the lateral area. Now, isn't that weird? Like, isn't that surprisingly complicated? That's a surprisingly complicated statement right there for this lateral area. Now, again, what's so cool about this in my mind is if you take it one step further and you chop the top off, like that's a coffee cup. So, you know, again, this is a very ubiquitous shape in our culture. So, you know, what's the surface area of paper it takes to make this cone? There's a lot of money associated with that statement right there. So, you know, you guys should be the people that can answer questions of that nature. So what we're talking about here is, you know, the ability to make that formula for ourselves. Now, I'll give you that one as extra credit. But again, what I'm concerned with here is not this, because pi r squared is the area of the top, which would be the bottom of your coffee cup because it's upside down. And then pi capital R squared would be the area here. What I'm concerned with is this lateral area. Like, could you build that formula for yourself for extra credit after I show you kind of the cone? And so what I'd like to do is just come up with, well, this area right here. Now we just did that, right? Except for it was even worse because it was a parabola, right? This is a straight line. All I have to do is take that straight line right there and spin it around the y-axis. I'm doing the same thing I just did a minute ago, and apparently I'm going to get that. Let's see if we can pull that off.
Well, isn't the r squared plus h squared, or the square root of r squared plus h squared, kind of similar to when we were just making a circle on Desmos and we type in the square root of y squared plus x squared?
It's absolutely related to that. So let's see, I did not pre-plan this. It seemed like a minute ago it was a lot easier to spin this around the y-axis, wasn't it? Wasn't it easier to spin it around the y-axis? I could put this on here any way I wanted. So I'm going to put it on like this and spin it around the y-axis. And of course, this length right here is r, and that height right there is h. So it's important to note that r and h are constants. I just haven't chosen them yet, because what am I really trying to do here? I'm trying to find a formula that works for all problems. I don't want to do this when h is 9 and r is 6, because then I got to do it over again for the next cone. I don't want to do calculus every single time. I want to do it once and for all with letters instead of numbers and get an algebra formula. So here's my slice. I'm not going to try to draw it 3D. I'd like you to take a second and try to set that up. Can you, based on logic, set up the surface area for that little slice, that little stripe? And remember, it actually goes over to the other side. Since this thing is actually going to spin. Just going to give you 1 minute to try to set it up. All right, I'm catching up. Do you agree that in this drawing, the radius of our ribbon is X? So the circumference of that ribbon, in other words, the length of it, when I stretched it all out, would be 2 times pi times radius, which is X. And then I just have to multiply by how tall it is. And it is our arc length formula tall. That's it. Everything is X's. Now just add all those up. Add all those up while X does what? Where does X go to? What values can X take on if it slides up and down in that cone?
Wouldn't it be anything?
What is it down here at the bottom? Isn't that the longest X can ever be? What's X down there?
R.
It's R. So that's the longest it can be. What's the shortest it can be?
0. Oh, yeah, R.
Yeah. So it makes it to 0. Like right there at the top, it's actually 0 tall. Do you agree with that? Cool. Now notice I can't cheat this time. So I hope I set up an integral because their R's and H's are constants. You know, and I won't be able to type those into the calculator. So I'm hoping I don't have to cheat here. By the way, I will just let you in on my brain right now. There's a part of me that's worrying that this problem would have been easier if I had drawn the cone this way. But I don't know. Let's go see. So the only problem here is really this, right? What do I need to do? What do I need to do to get that? Well, I've got to have some kind of an equation. I've got to have an equation that says y equals with x's on this side, right? Well, that's just a line. You should feel pretty good about that. So what is the equation of the line? Well, lines are y equals the slope. Isn't that a rise of h and a run of r? So there's the slope times x. What's wrong with that though? One small subtle thing wrong with that.
It's
A.
positive.
Yeah. If I went from here, that's a rise of h, but a run of negative r. Does that make sense? That's a negative slope. That's part of why I was thinking maybe this one over here would be better, because notice that would be a rise of h and a run of r. That would have been a positive r over h slope. And then what else is missing from my equation is the y-intercept. What's the y-intercept? You can tell me that just by looking at the picture.
H.
H. Notice this equation over here would have been y equals r over hx plus nothing. So that would have been a much easier equation. I'm a little worried that that might have been made my life easier, but let's just see what happens. Well, I got to take its derivative, right? I got to find y prime or dy dx. So fortunately that h goes away, and all that's left for the derivative of junk times x is junk. And so it's just negative h over r. And I'm squaring it anyway, so maybe it didn't make any difference. Okay, we're ready, my friends. I'm going to pull this 2 pi out front. I'm going to evaluate this from r to 0. I've got an x here. And inside here, I've got 1 plus, I'll go ahead and write the whole thing out this time. I'm plugging in the derivative and squaring it. Or squaring it just gets rid of the negative sign. Why is this not terrible? This actually might look terrible to you, but why is it really simple? Why is this really simple? What is this
R-
again?
R and H are constants, so can't you just add them?
Those are just constants. In other words, that whole square root is like the square root of 9. It's like just a big number. So this is kind of like saying, what's the integral of x times 5? It's just a number. Like I don't actually have to, like, I don't have to look at r squared and go, oh, the integral of r squared is r cubed over 3. It's a constant. And I'm taking the integral with respect to x. Those aren't x's. Do you see what I'm saying? So this is not terrible. So for that reason, I could actually just pull that whole mess out front too. 2 pi times the square root of 1 plus, actually I'm going to do one thing here just to save us a little time. If I wanted to add those common denominator, wouldn't that be h squared plus r squared divided by h squared? If I multiplied this 1 here, top and bottom, by h squared so that I could add them and have a common denominator, you'll see that'll make our life easier in just a second. Ah, that's an easy integral to take. The integral of x. There's not even a square root. Sweet. Why did that happen? Well, last time we had a parabola. Remember how it was x squared? And so there was an x left over under the square root sign, but this is just a line. And so when I took the derivative, there's no x at all. It's just gone. So it's a super easy integral to take. So, and I'll save a little time by, nah, I won't. Let's just do that later. So that's easy. I'm just rewriting this. Now I've taken the integral of x, which is x squared over 2. And now I just evaluated at r and evaluated at 0. So that means my lateral surface area. If you say lateral, you're just saying, hey, I'm not worried about the bottom. Lateral is like sides. Lateral in football is like throwing the ball sideways to somebody. So the lateral area then is just 2 times pi times the square root of h squared plus r squared, which I can't square root, but I can square root the bottom. The square root of h squared is h. And then this is r plugged in there gives me r squared. 0 plugged in gives me 0. And I was all excited until I stared at this for a second and I thought, wait, I don't think that's the answer. But let's go ahead and simplify it a little bit more. Do you agree?
Because the divide by h.
What's wrong with divide by h?
I can't remember, but is that in the surface area equation?
Yeah, we'll go back and look at it in just one second. Let's go ahead and finish it. I mean, maybe I screwed up. I don't know. We'll figure it out if we did. So those 2's cancel, and basically that's it. So I end up with pi r squared over h times the square root of h squared plus r squared. There's the formula, which is wrong. Now I've done math long enough when I get something like this wrong, I actually get, I don't know if excited is the right word, but it's kind of like, oh, cool. You know, there's a mystery here. In my case, because I've done math so long, I know my mistake is kind of stupid. But you know, what was that equation supposed to be? Not what we got. So we got the r squared plus h squared square rooted, but we got the 2 canceled and we got pi r squared over h. So it's like a little off, right? Dang. Anybody see anything wrong? Oh, I see something stupid. You guys should have told me this. This is stupid.
Did we mix the R and the H up?
Dyslexia happened right there. So for some reason I put R over H instead of H over R. Let's go fix that really quick. I'm just going to go erase it all. H.
I noticed
R.
when it switched because I was writing H over R, and then I saw that your paper had it the other way around. So then I just suddenly switched, and I was kind of like, "Oh, I must have been writing it wrong," and I followed along. But
Yeah,
that's
we're
where
like, oh, I'll figure it out later, right? And of course you should do that, right? Because I'm the teacher and I would be getting it right, wouldn't I? So that's an R squared. So that means this is an R squared. So then when I plugged it in down here, this was supposed to be an R. So that's helping. But I still lost that 2. So now this R cancels with one of those R's, and so that doesn't exist. Actually, I think this is actually correct. That's right.
And then we have 2 pi out front, right?
Yeah. The reason I said I'm suddenly remembering that this this is unfortunate timing, but I think I pulled up one of these that had a mistake on it. Like that 2 is actually not there. That 2 is actually not there. Interesting side note, you should recognize the Pythagorean theorem here, R squared plus H squared. Sometimes that slant height is called L, and so I've seen this formula written as pi R L. So L is the slant height. So we actually got it right. That 2 is not supposed to be there. But do you see what I mean about like what calculus really does? Do you see how we just found a formula thanks to calculus, thanks to the math that I'm teaching you right now? We just found a formula for all surface area of cones, and so now we don't need calculus anymore. We don't need calculus ever again here. So I saw that formula long before I ever understood where it came from. And again, I think there's two ways to look at this. I got to shut up, but one of them is that's extremely cool. I can build these formulas for myself. I don't have to just take them from people. I can actually make them. I feel powerful. I mean, that's neat. I agree. The other argument is, why do I need calculus? Like somebody's already made this. You're not wrong. Not only that, but in our era, we even have software that, figures this kind of stuff out. We got a phone like, hey Siri, what's the formula for the surface area of a cone? Like, it's amazing kind of the world we live in. So there's a great argument that says, you don't need this stuff. Because people have made algebra formulas for everything that's complicated. I'm teaching something in engineering that's just breathtakingly cool that involves integrals and so forth. Okay, I need to shut up. The other thing I wanted to show you that I'll show you at the start of tomorrow is, and if you want to think about this ahead of time, just to see if you can figure it out yourself, the surface area of a sphere, you may remember, is equal to 4 times pi times r squared. I wonder, my friends, could you stick a equation of a circle right there and spin it around the y-axis and do exactly what we've been doing today and generate that classic formula that you have seen before? Calculus is where it came from. It's not a terribly hard problem. Try it. All right, get out of here. As I said, stay after if you want to talk about the project or anything else. Otherwise, adios.